Today, I have the absolute pleasure, and I seriously mean it, to be joined by Keone Hon, who is a co-founder and CEO of Monad Labs. Keone basically isn't your average blockchain character. I did my homework, so his reputation builds on his unique background in high-frequency trading, and also his passion for operating infrastructure at the limits of what is physically possible. And he set out to revolutionize the industry with his brainchild, that is Monad, a high-performance, parallelized EVM layer 1 blockchain. So Monad, we were following Monad since a couple months already. Monad has been cooking, and today we tap into Keone's expertise to understand how Monad paves the way for a faster and more efficient future for decentralized applications. Keone, I'm stoked to have you, and thank you for joining us.
Yeah, thank you so much for that kind introduction, Dominic. Pleasure to be here today.
You're welcome. So to kick things off, I want to let you know that I really like the memes around Monad's community. I really dig the purple papers. And as an avid NFT collector, I also hope that there will be an NFT collection somewhere in the future. But let's see. So we have a lot of ground to cover today. I would suggest we start with a brief introduction of yourself. Maybe you share with us how you ended up in the blockchain or crypto industry, and what keeps you motivated and passionate about it.
Yeah, my name is Keone. I have been working on Monad for about 2 years, and before that was in the high-frequency trading space, working as a quant for about 10 years. So I started in HFT right after college, studied computer science, and then ended up joining a high-frequency trading firm called GetGo, was there for 2 years, and then joined Jump Trading in 2013. High-frequency trading is just about building systems from scratch, and there's a huge emphasis on performance, which I think is a great background for then trying to push the performance of crypto forward. Spent a number of years basically building up a trading team that ended up being a significant participant in a number of futures markets, such as the Chicago Mercantile Exchange, or CME, which is the biggest futures market in the world. And did that for a number of years, built systems from scratch, got tick-to-trade times down to sub-microsecond level, meaning that, over 1 million cycles per second of tick-to-trade possible. Packet comes in, decide how to update fair values for a particular instrument that we were trading, and then send an order out in less than a microsecond. Just a good experience, definitely really fun, and fun to work in a small team that was working on low-level systems engineering. Then ended up joining the crypto team at Jump in mid-2021, and mostly focused on Solana DeFi for about 6 months. And I think Solana made a lot of sense for our team at Jump because it was really performant, transactions were really cheap, and there was a new, different focus on user experience and making sure that, people who are not crypto native coming into the space for the first time could utilize high performance applications and pay very little in transaction fees in order to do that. And I think, seeing that the rise of Solana during the Solana summer, when the Degen Ape Academy NFT mint happened, and then there was kind of a Cambrian explosion of NFT projects launching on Solana. People could see that for the first time you could mint NFTs with really cheap fees and trade them with really cheap fees. So there's a lot of potential for mass user adoption out of that. So basically just kind of observing that and observing from the sidelines, it became really clear to me, as well as to one of my co-founders at Monad, James, who I started working with since 2014. We joined the crypto team at Jump together. We're working on Solana DeFi. We could just see that there's a huge need for more performant EVM. And it seemed like there's a lot of exciting applied cryptography research going on in the Ethereum space. There's a ton of interesting work going on rollups and data availability in certain other verticals, but it seemed like no one was really focusing on actually improving the execution system, or very few people focused on that. So we decided to leave Jump at the very beginning of 2022 and start Monad.
Okay. Hey, it's a super exciting background, especially the high frequency part. Just a couple of weeks ago, a colleague of mine suggested that I should read about the history of high frequency trading back then, when they started to move closer to the actual exchange, like physically, because they had such a big advantage by doing that. So yeah, great background. And I would suggest we start very high level, scratching the surface somewhat. You kind of outlined it a little bit, like what is the story behind Monad? Also, what is the story behind the name? I couldn't find how you came up. What does it have a certain meaning? And then maybe you could dig a little deeper on what exactly inspired you to create Monad. You said scaling issues and high transaction fees that kind of limit utility basically. And what specific problems are you trying to tackle with Monad currently?
Yeah, maybe I'll touch on the name first, just because that's the kind of the simplest thing. We just thought it was a good name. It's an uncommon common noun. In functional programming, a monad without getting into too many details, it's a component in functional programming. So maybe 1 in every 20 developers that we talk to is extremely excited about the project just because of the name. It's a cool concept. But then beyond that, a monad is also a fundamental unit. It's, I think in Greek, a single-celled organism, and just like a fundamental component. There's also some religious aspects where it refers to like the one God. So in general, like you could see like the mono part in it. It's the idea of like, the one ring to rule them all, or like one effort that could really change things.
Cool. There's a lot of to untangle in the name. I like it. So you really put some effort into the branding and the identity. Very nice. So interestingly, for this high performance blockchain, you went out and picked the EVM, right? Maintaining kind of bytecode level equivalence and also Ethereum RPC tooling compatibility. So now I would be keen to know, like, what were the reasons for you to stick with the EVM, and why did you not build your own EVM like other entities like Solana are doing, for example? And moreover, like, what are the trade-offs now of using the EVM? Like, what kind of boundaries you have to operate in now because you chose the EVM?
Yeah, I think the reason we chose to build for the EVM is pretty simple. It's that most developers are building for the EVM. So most applications, most developers, there's a ton of tooling that's been built out to support either the higher level languages that compile down to EVM or for the EVM itself. I think at the end of the day, the EVM and again, the languages that ultimately compile down to it, like Solidity or Viper, really have a strong network effect. Over 97% of all TVL in crypto is in EVM applications. And, there are other things as well. Like, people don't really think about the research aspect, but almost all of the applied cryptography research is being done in the context of the EVM as well. So it's really kind of the dominant standard. And there's a huge amount of demand for a more performant VM. That way, developers don't have to change anything. Applications don't have to be rewritten. If we can just make improvements under the hood to the execution system and basically upgrade the engine of the car without changing how the steering wheel works, so that people don't have to learn how to drive a different kind of thing, can actually unlock a lot of productivity for the space.
A great answer. Maybe we dive a little bit into the substance on what makes Monad such an outstanding solution. And I know there are like 4 major areas that we can touch base on. Let's go step by step. I would start with parallelization. So it's also like a mad tongue twister. Like for me, it's hard to to say it. But the word itself, like the term, gets thrown around like in a inflationary fashion already, right? Like projects are quick to jump the bandwagon currently. And for me, it's important to really highlight the projects that actually come up with disruptive and substantial improvements. And I consider Monad to be among these projects, because you are kind of like almost disruptive on plenty of verticals, right? So let's use some time here to debunk some misconceptions and outline what makes Monad so special in an environment where basically everybody tries to join the parallel kind of bandwagon. So let's start with the parallelization. As I understood, it brings improvement, but it's not the entire magic, right? That is happening around Monad. But let's start with parallelization. Maybe you could explain what that actually means to our audience, and why is it actually enabling us to achieve a higher performant blockchain?
Mm-hmm. Yeah, parallelization, and I guess maybe more specifically in Monad, optimistic parallelization of execution is basically the practice of running many transactions at the same time on separate threads and generating a bunch of pending results, which each track the inputs and outputs for that transaction. And when I say inputs, I mean basically the dependencies on state. So like, for example, if a very simple transaction would be a USDC transfer. So for example, if the first transaction in the block was like me starting from 100 USDC in my account, sending 10 USDC to you, Dominic, then, the inputs would be the balance of my USDC account, which is a particular address slot tuple, which currently has value 100. And then one of the outputs of that transaction would be updating that same slot from 100 to 90. And then, of course, there's also a second slot involved here, which is your USDC balance, which maybe is going from like 0 to 10. But let's not focus on that for a second. So in any event, parallelization means running a number of transactions in parallel and generating a bunch of pending results, which keep track of the inputs and outputs given that initial run. Then we step through those pending results one by one in the original order of the transactions and commit them if they're valid, or reschedule the work if they've since been invalidated due to one of the changes to one of the inputs. So maybe to make this a little bit more concrete in example terms, let's imagine that there's a Monad block which has a bunch of transactions in it. The transactions are still in the linear order, like similar to an Ethereum. And the job is to get to the end state after running each of those transactions one by one. But with parallelization, we run a bunch of those transactions in parallel. So for example, imagine that the first transaction is, like I said, me starting from 100 USDC and sending 10 USDC to you. That's transaction 1. Yeah. Transaction 2 is some other unrelated thing, like someone minting an NFT. And then maybe imagine that transaction 3 is me sending 5 USDC to another person. Let's call them Alice. So in optimistic parallel execution, what happens is, the first transaction gets executed. So the input is 100 and the output is 90 for that particular USDC slot. The second transaction is just, like I said, minting an NFT. And then the third transaction, when it's run optimistically, still has an input of 100 USDC and an output of 95 USDC. And then, so these are just pending results that are generated temporarily. And then we step through those pending results. So we get to transaction 1, pending result 1, we commit that, that's fine. We get to pending result 2, we commit that, that's fine. But then when we get to pending result 3, at that point we realize that that pending result wrote down an input of 100 and an output of 95, but now like that 100 has actually since changed to 90. So this input has become invalidated. We need to go reschedule that work.
Oh, okay. Is that also some kind of trade-off compared to a deterministic approach then?
Right. So the benefit of this, actually maybe one other thing to mention about that first. So when we're trying to commit pending result 3, and we notice that the input for that pending result was 100, but now since then the value for that slot should actually be 90. So we have to go re-execute that work. That re-execution is usually very, very cheap because that slot is already in memory. It's cached, so we don't have to go all the way back to the SSD to go retrieve that value. And in general, the re-execution of the computational steps, like in this case doing a subtraction, is not very expensive. So yeah, I mean, in terms of you were asking about the trade-offs, the alternative approach that I think you're referring to is one where all of the dependencies for every transaction are pre-specified as part of the transaction. For example, at Solana, every transaction has to pre-specify all of the accounts that it depends upon. There's also a proposal in Ethereum called the introduction of access lists, which is in place in Ethereum, but is not mandatory. So like in either event, that thing that you're referring to, like pre-specification of dependencies, what are the trade-offs between those two? I think there are a couple of reasons why we think that the optimistic parallel execution approach that Monad takes is the better one. Number one is because the transactions are smaller, because you don't have to have like all this extra information that has those access lists. And we think ultimately that network bandwidth is going to be one of the biggest constraints. So it's better to have smaller transactions that can travel over the network more efficiently. So that would be number one. Number two is that when you pre-specify dependencies, sometimes those dependencies are wrong because maybe the state has changed from the time that you sent that transaction until now. So, if the dependencies are wrong and you require that the transaction specifies exactly what it needs, and since then the dependencies change, that transaction is just going to fail. So it can result in unexpected failures and a bad user experience for users. There are a couple of other reasons, but I'll pause there in case,
Yeah, I seriously think it just clicked for me because, so if I think about just a processor kind of, so as I understand, you utilize now kind of a multi-core approach, right? Like when I think about a processor, you run a bunch of EVMs in parallel instead of sequential, and then kind of state sync before you commit to a block. And because you do that in an optimistic fashion, you don't actually have to identify independent transactions up front. Is that correct?
That's correct.
That's really cool. Okay. What percentages of transactions are independent currently? Do we have a number there? And do you think that will change in the future as the whole ecosystem becomes kind of more interconnected? We see that already with, for example, restaking, right? Now you have LST and then restaking, and now you put it in Pendle, and then there's like a huge daisy chain already of like state that is kind of interconnected.
Yeah, that's a great question. I think maybe another, the percentage of interconnectedness depends, and I think it's also a little bit hard to define because, if transaction 1 and 2 are related, but then 2 and 3 are not related, but then 2 and 4 are related, like what does that mean? How would you actually measure the interconnectedness? I think ultimately it's really just performance. Like the way to comment on like to what extent is this a problem is just to comment on performance. But I think, in the talking about performance for a second, another way to explain the parallel execution is to think of it as like kind of 2 phases. So the first phase is, actually, before I even say that, like, let me just emphasize that the single biggest bottleneck in execution is not the computational steps, it's retrieving state from disk.
Yeah.
So like, CPU time is pretty cheap. CPUs can do a lot of computation. It's really easy to add numbers together or multiply or generate hashes, etc. All of that is happening in nanoseconds per instruction, or even less than that sometimes. But state retrieval is what's expensive, because if you have to go to the SSD to retrieve a value, that's 40 to 100 microseconds, aka 40,000 to 100,000 nanoseconds. So just like way, way more than the cost of compute. So at the end of the day, the single biggest bottleneck for executing any transaction is going to disk and retrieving it. And this will kind of play into like maybe the next topic that we talk about later, which is MonadDB. But before I go there, I'll just say, like, on the topic of parallel execution, you can think of it as two separate phases. The first one is running a bunch of transactions in parallel. Running each of those transactions basically surfaces all of the dependencies for that transaction. So it means that then when that thread is running, that VM, it's like realizing, oh, we need this piece of state from SSD, so let's go retrieve it. And when that data gets retrieved, then it gets put in the cache. Cache is way faster than SSD, just to be clear. So, the first stage is like running a bunch of transactions in parallel, generating pending results for each of them, and also surfacing all of the dependencies and pulling those into cache. And then the second stage, which is stepping through the pending results one by one, is either for each pending result, like immediately able to commit it if there's not been any changes, or if there have been some changes to some inputs, then it's re-executing. But when re-execution happens, those dependencies are generally in cache. So they're much, much faster to re-execute than they would have been the first time, because they don't have to go back to disk.
Very cool. It reminds me a little bit of entropy that we know from physics, kind of these interdependencies. Like I imagine they only get more. But yeah, let's touch base on where Monad really starts to shine. And yeah, it's what you mentioned already. It's the Monad database. So if we explore the verticals where we can optimize aside from parallelization, one of the pillars actually is state access via optimized databases, right? I know other players are also trying to come up with like innovative database solutions like Sci or Avalanche to gain increased performance. And as I understood, the Monad database is actually the enabling puzzle piece for optimistic execution. Is that correct? What makes Monad's database so exciting?
MonadDB is a completely from scratch database written in C++ that's specifically designed for the problem of storing Ethereum Merkle tree data on SSD. So, Ethereum state is all stored inside of a Merkle tree, which means that at the end of every block, there's a Merkle root, which is like a hash at the very top of the tree that is computed based on all of the values in that tree through kind of iterative, compute a hash on all the children nodes in the tree to generate the hash of the parent. And then, combine that with other siblings to then generate the grandparent's hash all the way up to the top of the tree. The Merkle tree and the fact that Ethereum has a commitment to all of the state in the form of the Merkle root is one of the sort of fundamental pillars of Ethereum, because it allows other blockchains or other systems to interface with Ethereum while being assured that all of the state is that, different nodes that basically have the same Merkle root have all of the same state. So it's basically like a commitment to all of the state in a very abbreviated, very efficient format. Merkle roots can't be unpacked. That is to say, if I just give you a Merkle root, you can't unpack that into like the entire tree. Of course, like just logic would suggest that a Merkle root is very short. I think it's 32 bytes, whereas the Merkle tree, all of that state is massive. But it you can verify that a value in the Merkle tree is what it is if you know the root, due to something called a Merkle proof, which we won't get into. But anyway, the point is that there's all this state that lives in Ethereum, which represents everything, like all of the states of every smart contract, everyone's account balances, everything. And transactions, they require small parts of that overall global state in order to proceed. So like I was saying before, processing a USDC transfer requires knowing what, my USDC balance was before that transfer, and then requires mutating that balance into a new value. And that's a very simple example. There are a lot of other ones. And at the end of the day, because this state is pretty big, like in Ethereum, it's over 100 gigabytes. So it kind of, it has to live on an SSD. It's not feasible for all of it to live in memory. And if, all of this state is on SSD, but if it's expensive to go retrieve that data from SSD, then it's just going to be hard to like execute very quickly, because there's a significant cost to like going and retrieving data in order to be able to proceed with the execution. So MonadDB is basically a way of making data that lives on SSD, like this overall global state, to be much more efficiently accessed. I think the really like dumb description of MonadDB is that it's enabling parallel access to the state. So when many virtual machines are running in parallel in Monad's optimistic parallel execution, those VMs can all make calls to the state and like retrieve values from there in parallel, as opposed to with existing blockchain systems which use commodity databases where there's a bottleneck in terms of the access to the database due to lack of full support for asynchronous I/O in these databases.
Yeah, that makes perfect sense. Very, very exciting. That so what you're saying is now we have these two parallel execution, but also parallel access enabled by the MonadDB. And kind of the missing puzzle piece that we didn't touch base on is now the Monad consensus, right? So it's kind of another piece that you are optimizing, or that you crafted in a very elegant fashion in order to allow this the Monad blockchain in its entirety to be highly performant. Maybe you could explain what is new with the MonadBFT compared to other cool consensus mechanisms like Snowman or Tendermint or the like. And I also know I read somewhere that there's still some kind of research needed when it comes to prevention of spam attacks. Is that correct? Or
yeah, well, let me start by describing MonadBFT really quickly. So MonadBFT is a derivative of the hot stuff consensus mechanism. Hot stuff is a performant consensus mechanism that generally operates with linear communication between nodes, meaning that if there are n nodes in the network, then there's like, a multiplier of n messages that need to be sent. So in particular in hot stuff, it's a leader-based algorithm where the leader comes up with a block proposal, sends it to all the other nodes. All the other nodes evaluate that proposal and then vote and send their vote directly to the next leader. So it's kind of a fan-out, fan-in approach where the leader fans out to everyone else and everyone fans in to the next leader. And in the happy path, like as long as things are running smoothly, there's no need for all the nodes to message all the other nodes. If that, in other algorithms where it is necessary for all nodes to message all other nodes, it basically means that the communication complexity becomes O of n squared, aka quadratic complexity, which then severely limits the size of the network in terms of the number of nodes that could participate. So like in Tendermint is a quadratic communication complexity algorithm, and you see that most Tendermint chains are about 100 nodes participating in consensus or less because of that communication overhead. With Monad, we felt that it was really important not only to have really performant consensus, but also to be able to scale the network to hundreds of nodes.
Okay, very cool. I think one piece is missing that I wrote about. What is Superscalar pipelining? I think that makes the picture complete, right?
Yeah, so that actually kind of is a good segue to also the other question you were asking about, which is spam attacks and, where that comes in, what the concern might be and how Monad has addressed that. So pipelining is the practice of creating multiple stages of work and then intelligently pushing work through those multiple stages so that the work can proceed in parallel. So a really simple example of this is like, say that you have 4 loads of laundry to do. Then the naive thing to do would be to, do everything for the first load before starting on the second one. Like, putting the first load in the washer, then moving it to the dryer, then folding it, then moving it back to your closet before starting on the second one. But, everyone intuitively understands that it's much smarter to, as soon as you move the first load to the dryer, then put the second load in the washer, and kind of progress all of them in parallel. That's really all that pipelining is. It's just creating multiple phases of work so that we can utilize all of the resources of the computer as efficiently as possible. And in the context of a blockchain, one obvious thing that comes up is blockchain has at least 2 major components, which are consensus and execution. And in most blockchain systems, those 2 are interleaved, meaning that the nodes have to execute before they come to consensus. And this has a kind of bad property that actually very much limits the time budget for execution, because in practice, consensus ends up taking up most of the block time. So for example, in Ethereum, the block time is 12 seconds, but the rough time budget for execution is only 100 milliseconds. And the reason for this is because consensus and the process of, all the nodes in Ethereum coming to agreement about that block, that's very expensive. So it means that there's actually only a very small portion of time that can be set aside for execution. But 100 milliseconds in 12 seconds is tiny. It's 1%. So literally, like, there's this situation going on where there's a time dilation factor of 100x, where even though, the block time is 12 seconds, we only have a very small portion of that time to go execute. So if we could somehow address this, then we could actually massively raise the budget for execution, and utilize the full block time. And the way that we've done that in Monad is by introducing a concept we call deferred execution. So the idea is basically that first the nodes come to consensus on a block, and then once that happens, then 2 things happen in parallel. One is that we start doing consensus on the next block, and the other thing that happens is we start executing the list of transactions that we've just consensused on. So in effect, like, the pipelining here is that there's multiple swim lanes, there's consensus, and there's execution. And as soon as we complete consensus on one payload, like one block, then we can start executing it. But in parallel, we can do consensus on the next one.
Pretty much reminds me of assembly lines, right? That were back then invented by Henry Ford, just on a super cool computer science level. Very nice.
Yeah.
So as I understand, if we kind of stack all of these innovations, being MonadDB, parallelized execution, the Superscalar pipelining, and then your new, highly innovative consensus mechanism, it results in this very performant integrated blockchain. The space likes to compare metrics. Maybe can you throw some numbers at us, like what TBS can we expect? Where will the fees range? I know it depends on block space demand. Then maybe also how many validating nodes will be possible? Is there a limit with Monad or not? And then I think you tackled it before, but I'd also be keen to know, since I understood with MonadDB, you still have to store all of the data. How do you tackle state bloat at some point in the future? Will it become a problem, or is this space just no problem? It grows faster than state bloat, maybe.
Yeah, all the important questions. Monad at Mainnet will offer over 10,000 transactions per second of throughput. Or actually, the number that I like to think of is more like transactions per day. So Monad will offer over 1 billion transactions per day. And those are full transactions, not just token transfers. I think one way to kind of inflate the numbers of a blockchain is to just test only using token transfers, which are way simpler. But with Monad, the back test is the historical history of Ethereum. So over 10,000 TPS of throughput, 1 second block times, and single slot finality. I think what this results in is much, much, much more block space than with some existing networks, like you mentioned, which ultimately results in much lower costs for end users. So we currently think that a transaction that costs 100,000, or that has the complexity of 100,000 gas, which is about the complexity of a Uniswap v2 swap. So that kind of transaction generally costs $5 to $50 on Ethereum mainnet right now, and on the order of 10 cents to $1 on existing Ethereum L2s that are using Ethereum for data availability. On Monad, we expect that transaction to be a fraction of a cent. So orders of magnitude cheaper, coming from orders of magnitude of higher throughput.
Very nice. Recently, I studied a little bit. You released hardware specs for nodes, and frankly, I was pretty impressed on how reasonable they appeared. Like they were actually quite doable for the average, let's say, retail node operator. I feel it's quite a significant USP for Monad already if you manage to optimize at that magnitude on multiple venues while keeping hardware requirements comparably low. And I also imagine it being a very thin line in balancing these hard engineering problems with the resulting hardware specs that we see right now. However, there are always critics or controversies, and it's fair that, like, some argue that prioritizing performance only might at some point, or to some degree, like, compromise decentralization. I know the trilemma is not that big thing as it was anymore, but what's your take on that? Like, is it an issue or not at all?
Yeah, well, I think maybe a related question, which you asked before, which I didn't get to just because I paused, was about state growth. So just to maybe touch on that for a second, because it's very related to what you were asking as well. Right now, like I said, Ethereum state in aggregate after 10 years of Ethereum running is over 100 gigs of data in the active state. Of course, the transaction history is larger, but what we really care about is the active state of Ethereum. And like I said, that state lives on SSD. And the critical problem to solve with respect to execution is making that state more available, if you will. It's almost like the state availability is like the problem that we're solving here in Monad. So MonadDB makes state much more available, much more efficient to be accessed for the purposes of execution. And that's because this custom DB that we've built from scratch is specifically optimized for storing Merkle tree data. It supports parallel access, so that then when multiple VMs are running in parallel, they can all read different parts of the state tree in parallel. I think the thing to know about SSDs is that they're actually like really cool pieces of technology that are really performant. It's slower than reading data from memory, like I said, 40 to 100 microseconds, but they're pretty wide in terms of bandwidth. So it's like a high latency but high throughput kind of storage offering, but you need to have software that appropriately allows all of that width of data transfer to happen efficiently. With existing databases, like Ethereum uses LevelDB, Solana uses RocksDB, these requests basically get marshaled through a single pipe, which means that when trying to make reads to many different pieces of the state tree, those reads end up blocking each other, and the access is quite slow. But with MonadDB, it just makes it so that a lot more data can live on the SSD, and can live in this state tree that's growing and growing without concerns about the cost of those accesses degrading as the state tree gets bigger. So kind of to bring it back to your original question, like, I know a lot of people in Ethereum are concerned about state growth. I think state growth, two things. One is, like, in some senses, fundamentally a reflection of user adoption. Like, if you have Aave with, 100,000 depositors in it, the state is going to be a certain size. If there's 10 million depositors, it's literally just going to be bigger. Like, that is actually a reflection of adoption. But it's understandable that people are worried about state growth because right now, like existing clients are using an existing database system with an existing database schema built on top of that, that's really inefficient and that actually gets more inefficient as the state tree gets bigger. So, that motivates people to be very worried about state growth and want to limit the throughput of Ethereum in order to limit the state growth. But if you change that calculus fundamentally with a new database, like a 0-to-1 innovation of a new database, then a lot of that calculus changes.
Okay. That's an exciting outlook, to be honest, right? Very cool.
And sorry for the long answer on that one also, but I think it's just important to keep in mind that like a lot of our assumptions are somewhat predicated on the existing set of tools that we have. So if you have a new tool, the new tool can actually make us much less worried about state growth, for example, or at least like enable state to grow to the size of the SSD, which is like 2 terabytes on Monad's hardware requirements, which is much, much bigger than the current state right now.
Yeah. And 2 terabytes is not crazy, to be honest. It's not a huge hardware requirement in my opinion.
Yeah, it costs about $200 to buy a 2 terabyte SSD.
Yeah, as I said, it's very reasonable. I even, if that's possible, I know testnet is coming somewhere in the not too distant future. I will also look into running a node if that is possible. If it's So let's look a little bit into kind of other approaches. There are strong voices out there, you know that, and I think we should discuss it and have some and get your take on it. Because like not only monolithic or integrated approaches benefit from optimizations at the VM level or at the client level or from faster hardware, but also validity-proven execution layers, correct? I'm going to cite Polinia here, who recently, it's a couple months back, he, quote unquote, every single monolithic blockchain seeking scale will upgrade to tech like validity proofs and data availability sampling or risk obsolescence. So I'd be keen to know what is your perspective on the future of validity proven execution layers, because they come with a lot of benefits too, as they allow for very low latency, bandwidth requirements, the possibility to verify the integrity of all the transactions from mobile devices, which is like super nice, right? And they also come with potential cross-chain composability via proof aggregation layers. So will Monad at some point look into this kind of technology as well? Or does it not make sense? Yeah, what's your take on that?
Right. So I think
are you not a fan of validity proofs? I'm just keen to know what you think about it.
Yeah. So I think that the way that I think about it is there's Ethereum L1, which currently has a bunch of, L1 specific state. For example, like, Aave is deployed on Ethereum L1 and there's a bunch of accounts. And then all of the nodes in Ethereum know about all of the state that's directly on L1. But rollups kind of give us a different style of scaling, which is fractal scaling, whereby there could be like a separate rollup, basically a separate blockchain who has a whole bunch of, unpacked state on it. Like there's Aave deployed on an L2 and all the balances there, et cetera. But then there's just a mechanism that kind of summarizes all of that state, which is very verbose, of one of those like L2 blockchains and condenses it into just a single Merkle root on the bridge contract on the L1, which is like a commitment to all of that state. So I imagine it being like an entire world that is being carried around in, Inspector Gadget's briefcase. And, so it's very compact. Like it doesn't take up a lot of space in our world, but like, the other world is like, in some senses, like in his briefcase, just walking around on Main Street. But, the way that unpacking, the packing works is that, we can basically verify that something that particular state on the L2 is true. We can verify that on the L1. but we can't actually like unpack the briefcase itself while Inspector Gadget is like on our world, like, because obviously unpacking it would then unpack to something else that's equally the size of our world, and that wouldn't work.
Yep.
So the fractal scaling is just all about like state commitments. But at the end of the day, like if you want to actually know the values of any particular state, like if you want to know your deposit on Aave, you actually have to go interact with an L2 node, which is maintaining all of that state, processing all of that stuff. So yeah, I mean, I think it's like a good mechanism. Basically, like the whole rollup mechanism is the facility that like creates this briefcase for Inspector Gadget that like shrinks stuff down and like, creates those commitments. But at the end of the day, like the problem of like actually having a world that operates efficiently, that has a full, ability to like process all of the work that's being done on that world, that's a separate consideration, like the consideration of execution. And that's actually really what Monad focuses on, is making execution really performant, so that any world, whether it's an L1 or an L2, could do much more work and maintain much more state sustainably.
Okay, fair take. I mean, do you think, like in your opinion, is it possible? Say, I mean, the end game for our industry is basically to onboard almost everything, right? Be the internet, onboard, be the rails for the financial system, be the base layer for value transfer, like all of the crazy nice stuff that blockchains enable. So the end game is at some point we want to onboard the entire planet. Can we do that on one single monolithic chain? And if not, I know Monad already announced a lot of very exciting partnerships with Axelar or Layer 0 that you implement, I think, basically from scratch. So if not, like, do you think we at some point also solve the trade-offs or the risks that we have with cross-chain bridging as of now? Or do you think it's possible to onboard everything, to that everybody like has one shared state? Like, what is Monad trying? Is it possible to onboard like 8 billion people?
Right. Well, like I said, Monad currently has the ability to support 1 billion transactions per day of the typical complexity of current Ethereum history transactions. In the future, I think that future improvements that we're working on right now may push that to, several billion transactions per day.
Wow.
But as you're kind of hinting at, that's probably still not enough to onboard all 8 billion people and support all 8 billion people. Like if people are using blockchain apps for everything, like for personal finance or achievements or like ordering Ubers or like, I don't know, like paying for internet, whatever, like all these different things, that's, a couple billion transactions per day is not going to be enough for all 8 billion people, of course. I think at that point, there will be multiple monads as well. So a monad is really just, a very computationally dense network. It's a single fundamental unit of blockchain, but there could be many monads that are more like application specific or sector specific or regional specific. But the exact division doesn't matter and will just evolve over time. But I think it is important for each one of those units to be much more computationally dense than existing units are right now. Like Ethereum is processing 1 million transactions per day. So there's a huge improvement going from 1 million to 1 billion. You're going to get much closer to be able to serving all 8 billion people with a reasonable number of networks if each network can support 1 billion or a couple billion transactions per day, as opposed to if every network can only support 1 million or a couple million transactions per day.
Yeah, we will see. Like it's still a little bit unclear, right? How the space evolves. Of course, it's very obvious to me, like how big the benefits are of having one computationally dense monolithic blockchain, right? You have so much less issues. Of course, you have to operate at the physical limits, your hardware, and you might need a more performant node at home. But then you solve all of these composability problems and the fragmentation problems. So it's definitely, if you can make it happen, I think it's the most elegant solution we can have. Because on the L2 side, then we face all of these fragmentation problems, be it even at the community level, right? then you have all of these little fragmented communities that almost behave like religions or something like that. But yeah, very excited to see where Monad is taking, how Monad will change the game. And as we inch closer to the end of our interview, maybe you could outline like what's the current stage of development for Monad, and when can we expect to see the first apps running on the platform?
Mm-hmm. Monad is in active development right now, but I think you can expect the first public testnet in Q2 of this year. And then we expect that we'll be running testnet for about 6 months. So you can expect Monad by the end of Monad mainnet by the end of this year.
Okay, exciting. So I have to get my hardware ready, I guess. Yeah, so to our audience, if you're interested in learning more about Monad and Keone and what Keone and the team behind is working on, be sure to visit their website, follow them on their social streams. I will post links in the video description. Keone, honestly, it was an absolute pleasure to host you today. I think we, despite diving a little bit deep and in more complex territory, I think we navigated the discussion to be both engaging for the worst crypto natives, but also being accessible for the less advanced viewers. I am convinced that the audience gained valuable insights today. And on behalf of Bitcoin Suisse, we are very thankful that you shared time with us. Best of success for the upcoming internal testnet. And as I mentioned before, I'm very excited for Monad.
Yeah, thank you so much, Dominic. It was a pleasure to be here. Yeah, thanks for having me.